morning, Doctor.
Bismillahirrahmanirrahim. Dengar tak? Hello?
Dengar.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning,
Alhamdulillah.
all part-time students. Okay. So today is the first class of the mkem1763 System Identification and Estimations. Okay. Previously, I believe that you have two class before, which is the autonomous mobile robotics and linear system theory. So, and today is my turn as elective subjects. Okay, elective subjects meaning option subject pilihan. Linear system theory is the core subject, wajib ambil. Autonomous mobile robotics is an elective subject as well, is option subjects. So basically, system identification and estimation is, I can say that is empirical modeling of control system. Okay, mean that we are building mathematical model based on experimental data. Previously, that you learn during your undergraduate is the first principle. Okay, first principle modeling using all the theories that you learn during your undergraduate. So you have to use differential equation, derive Laplace transform, Z transform, and so on in order to get the final mathematical model. Okay, so in this lecture, I will give some introductions, objectives, synopsis, outcome, syllabus, lecture planning, assessment, timetable, and references. For your information, our lecture are recorded. Okay, so once it's finished, so I will upload in the YouTube. Okay, then I will give you the YouTube link for you to look again, watch again. Okay, during the class if you miss. So I am the lecturer for the subject. My name is Muhammad FUA'AD. Graduate from UTM in Electrical Engineering 1989. Considered as a cool school. Then Master's Control System in Sheffield in 1993. And my PhD in Instrumentation in 1996. I have 30 years experience as academicians. And part of that, I've been hold several admin posts in the Department for Off-Campus Program, 1999-2008, the Department of Control Instrumentation Engineering Department, 2011-2012. I was the academic manager for Master Top Course, 2012-2014. And I was the Dean of UTM Space, 2015-2018. Then currently, I am the head of research group, okay, Proton-I, Process Tomography Instrumentation, 2019 until now. So in terms of professional body, I also active in the professional body, which is a senior member of IEEE. IEEE stands for Institute of Electrical and Electronics Engineering. I am the Deputy Chair of Control System Society, CSS Malaysian Chapter IEEE, and the member of IET, Institute of Engineering Technology. So how to contact me? So you can contact me via my email. Okay, FUA'AD@fke.utm.my or phone 555-7216. So at the moment, for the last 3 weeks, we are work from home. So now also we work from home. So I'm in my home now, in my in my room office. On top of that, we have a WhatsApp list. So WhatsApp list is the main communication currently, beside emails and phone. So all items will be communicate via WhatsApp. I hope all of you are comfortable with that kind of communication. So in terms of publications, you can refer to my Google Scholar, right, by click the link that given, and Scopus index as well. Then all the materials will be parked in the mkem1763, which is the my personal website. So if you look at the program structure for mkem1763, so mkem1763, all of you, about 6 or 7 students, are the last batch of mkem1763. This is the old curriculum. Okay, for next year in March intake, so the program will be changed to MEEM. Okay, MEEM, not MKEM anymore. Which MEEM offered 1 year courses, fully detailed in 1 year time. Okay? That will be launched in March in 2021. So as I told you before, for this program structure consists of 4 subjects, core subjects, which is advanced instrumentation and measurement, linear system theory, discrete time system and computer control, and design of microprocessor-based mechatronic system. And from this, you have to choose 5 courses, okay? 15 credits may include 1 course from other program, meaning that 4 course, you have to choose MKEM elective subject, which is you already choose 1763 system ID and estimation, and I think is autonomous robot 1883. So you have another 2 subjects for elective. Okay, you can choose AI, you can choose set tuning, you can choose multivariable, and so on. Depends on the course coordinator. You can have to discuss with the course coordinator. And then another 1 course, if you want to take MKEM, also can. But some students, they would like to take other elective subjects from other courses, which is the MKEP on the power system, and on the MKEL, or the Master in Electronics Engineering, Electronic Telecommunication Engineering. For example, student might choose on the, what do you call that, wireless communication technology, which offered in MKEL, or maybe in power system engineering in MKEP. It depends on you if you want. If you don't want, you simply can choose 5 from the MKEM elective subjects. And then after you finish your subjects, about semester 2, you will be taken the MKEM projects, which is part 1 and part 2. Research project proposal and research project thesis, which is a total of 10 credit hours. And then you also have to take the other required subjects, which is university subject, one university subject, and introduction to research methodology in electrical engineering. So we come back to the subjects. The objective of the subjects actually to expose students regarding the theory of system ID and estimation. And at the same time is to introduce students to the basic concept of reverse modeling, or sometimes we call it as empirical modeling, including experimental protocol, test signal, model structure, parameter estimations, and model validations. So this course is an introduction to the system ID and parameter estimation. It covers all the system identification procedure, starting from data collection, pre-processing data, non-parametric model, parametric model, analyzing, validating, and converting models, and system identification case study. So we will go one by one on the certain case study. Is about 4 to 5 case study. So the abstract of the subjects or the synopsis, is required depth understanding of control system, modern control system, and digital control system. So maybe some of you already left your undergraduate quite some time, so no worries about it. I will guide you step by step, okay? So that you can understand the subjects as good as possible. And then the emphasis will be on the theoretical basis as well as the practical implementations. So the key components are the time response analysis, frequency response analysis, correlation analysis, power spectrum density, model structure, parametric model, parametric estimation method, test signal generation, and model validation method. So for the program educational objective for master's program, MKEM, we have about 4, okay? So this one is written in the, what do you call that, the prospectus of the School of Electrical Engineering, okay? You can read by yourself. And then the program learning outcome for MKEM. So we have about, Azim. So we have about 6 program outcome. Okay. Firstly, is on the advanced knowledge, demonstrate efficient proficiency, and then able to solve critical problems, able to plan, perform research undertaking, able to communicate, and able to continue lifelong learning. Okay, that is the PLO for MKEM. For these subjects, we have a course learning outcome. So there are 3 things, 3 different things: program educational objective, program learning outcome, and then course learning outcome. So program educational objective is a general master's degree program. Program learning outcome is for the MKEM, and course learning outcome is for the subject that you take today, which is mkem1763. So we have about 3 course learning outcome. First is able to explain the fundamental basis of system ID. And then number 2 is able to comprehend the fundamental basis of parameter estimations and able to apply both fundamental in a real case study. So this is at the moment for this semester, I teach the same subject but full time. So in this class, we have a lot of international students from Sudan, from Yemen, from Egypt, from Nigeria, okay? All are in the class, but they are not in UTM. So they are following the full-time timetable, which is on Wednesday from 2 to 5, okay? In local time, Malaysia time. So if my students stay in Nigeria, it is about berapa 7 to 8 hours different from 2 PM, earlier than that. Maknanya dia punya kelas tu dalam pukul 6 pagi di Nigeria. But for your class, okay, so this is the timetable given from the coordinator. The coordinator is PM Dr. Professor Madia, Dr. Salinda Bunyamin. So he arranged the timetable. So today, week 5, we are here. Okay. So it's class today, 10 to 6 p.m. for today and 10 to 6 p.m. for tomorrow. So actually, I don't make my class until 6 p.m. For today class is 10 to 1 p.m. Due to I have other subject clash on the 21st of November in Penang. So the class will be start at 2 p.m. until 6 p.m. So our class today as an introduction and some basics of chapter 1 will be given from 10 to 1 p.m. And tomorrow we will continue 10 until you are able to receive my lecture lah tapi tak adalah sampai 6 p.m. lah about 2 macam tu kita dah rehat dan kita bagi sedikit assignment untuk pelajar buat. Okay, is it okay? Senyap je.
Okay doktor, okay.
Okay, jangan tidur pula. So seterusnya after 21st and 22nd November class, so we will see again before Christmas, 19 to 20th December. So ini ada ujian rasanya, minggu 9 ni ada ujian. Okay, so all the tests will be implemented using e-learning and Zoom. Okay, so e-learning, you will collect the exam question, the test question, download it, and then submit through e-learning at the time given, about half an hour. Katalah kita mula ujian pukul 2 dan kita tamat pukul 3:30 petang, dan 3:30 sampai pukul 4 petang tu adalah masa untuk awak PDF kan jawapan awak dan submit kepada e-learning. Semua ada e-learning? Everybody have e-learning? Ada?
Yes, okay.
Ada
Ada.
Okay. Right. So similarly in test 2 also we have we have a test 2, okay, and then using e-learning and Zoom, and then we have some presentations at the end of the minggu 14. Okay. Dan exam adalah pada bulan Februari, okay, next year. Okay, clear? Right, this is the assessment for full time. So ignore it, okay, please ignore it, full time. Yang part time adalah yang ini. This is for part time, okay. So test will be on the 19th December, Saturday, okay. Then test 2 will be on the 23rd January. 23rd January, use di mana ni? Tak betul ni. 23rd January ialah berapa bulan tu? 23rd January. 23rd, tengok timetable tadi lah. 23 Januari pukul 2 juga. Okay. 2 p.m. Okay, pada 23 Januari. So we will update the test time, okay, all the details in the WhatsApp. Everybody subscribe WhatsApp. So total number of how many students currently? So we have one Umar, Sivananta, Zulafi, Nur Fariza, Daniel, and Hazim. All are local, not international. Then final exam February 2021. So this is part time. So this is the content of chapter 1, introduction to system ID. So we will touch on the introduction, model, application of model, okay, and some why we have to use empirical modeling instead of first principle modeling, And then in chapter 2, we'll see on the time response, frequency response, impulse response, correlation, frequency spectrum, and PRBS signals for identification. And then we will go for chapter 3, which is the parametric model representation, okay, type of parametric model and linear model and non-linear model. And then semester break, I think kita tak ada semester break, kita carry on sebab kita part-time. Then chapter 4, we will go on the parametric model, okay, which is estimation method, some method which is least square, generalized least square, recursive least square, predictive error, model validation method, and so on. And then we will end this course with chapter 5, case studies, okay, using data, real data from a hot air blower system, hydraulic actuator system, pneumatic actuator system, biodiesel engine, DC meter control, and so on. Source of data is from the internet. We should share from some university from Belgium. Okay, we will use some data from there. So for reference, we have about 3 main books. Okay, the first one is the Principle of System ID, Theory and Practice, 2017, which by Arun K. Tangirala. Okay, this is a good book, very good book. It's 800 pages. So I will give the book chapter from time to time if I feel that the book chapter is relevant to your study. And then the old book is Aljong in 1999, and the Soderstrom book is in 1989. So this is the book by Arun Tangirala, okay, Principle of System ID, and then the Soderstrom book, and then the Leonard Jung book, and some other books which is listed here also can be referred, okay, during your assignment or during your study, which is listed here. So to wrap up what I mentioned in the profile introduction, identification is the task of using input-output data to build a mathematical model. And this mathematical model is abstraction of the process, okay? So I can say that, okay, you are given unknown process. So unknown process can be any process, any system. It can be a car, it can be a motorcycle, it can be any logic or process plan, okay, which is we want to make a mathematical model of it. So what we do is we will inject input signal, okay, that we generate using hardware or we generate using a software program. Then it goes to the input of the process, and then the output of the process will be tapped, okay, will be observed, will be captured, and both of it will go to the identification process. Okay, all the data will be captured, will be pre-processing, will be analyzed, and then will be give a suitable model structure and come out with the model. So this model is estimated. Okay, we just estimate. Okay, the real one is this. This is the real one. Okay, real. Okay, the real one that we having, the process is real, and the input is real, the output is real, the measurement is real. And then we come up with the model. The model is the estimations, or we call it as simulations. Okay, we calculate this as numerically, okay, and experimentally, and it must be equivalent, as close as possible to the process that we estimate, right? So application of model in process system engineering can be divided basically into 4 main purpose, 4 applications. First is for design. So why we want to apply the mathematical model application it? Because we want to design the controller. Okay, we want to design the controller that can operate the process the way that we want. That's why we need to do some simulations, optimizations, planning, scheduling on the process in order to do the design. Basically, the basic design is the PID controller, okay? Or maybe higher than that, fuzzy logic controller. And then we need to estimate the parameter or the coefficients of the mathematical model. And this kind of estimation, including predictions, advanced process control, source sensors, filtering, and others. And at the same time, we applied a model for control. Okay, because we want to control the system, we want to know the stability of the system. Okay, you want to do some design of the controller, you want to perform some analysis and take some assessment from the process, the data that we capture. And it is the lastly is application of model is for monitoring purpose, where we want to monitor the statistical quality control of the process, and then we want to detect is there any fault detections or any diagnosis. Okay, fault detection is very important because when we have a process of a dynamic system or maybe static system, we need some maintenance. Okay, process cannot go until 100 years. After 5 years, we have to do check. It's similar to like a car that we drive. Okay, after 5 years, so some parts starting to broke, some parts starting to not function as well, including all the sensors. Okay, that's why we have to estimate the fault detections by taking the data, and the data we monitor the data. If there is some indicator from the data, meaning that it's not working, so it will give an outliers data. The outliers data is the sign that the parts of the system is not working anymore. So in order to do that, in order to do the mathematical modeling, we have two ways. First is the first principles, or we call it as the fundamentals. The second part is the empirical, or we call it as the data-driven. Data-driven meaning that we have the data. The data will speak for itself. Okay, so in fundamentals, we have to write the conservation equation, the constitutive law. For example, Kirchhoff law, Kirchhoff current law, Kirchhoff voltage law, or in mechanical is Newtonian equations, in chemical engineering is the mass flow equation, and so on. So we have to understand the fundamental, then we derive the equations, and then we come up with the differential equation and transfer function or state space model that represent the system. And this one is quite tedious because it's fully mathematics. Okay, but at the same time, we also can take the process, we give an injection of input, then we tap the output. Input and output data we collect, and then we perform analysis or experimental, perform experiment, propose a model, and we estimate the parameters, and then we compare. We compare, then we can see that it can be close each other, okay, in terms of structure, in terms of the parameter coefficients. That's why the real process is something like this, where you have a process, okay, unknown process, and there is a disturbance, of course, okay, is a noise from outside of the process. Okay, this may come from your headphone, this may come from your 3-pin power plug, which have a 50 Hz noise. It can come from other noise, okay, which is uncontrollable, uncertainty, unpredictable, and so on. Then we measure, okay, the disturbance enter the process. We measure the input and the output. Then the sensor will measure the output, okay, and give information, a feedback to the system, and then the signals that we set and the output error will be compared together in comparator and give information to the actuators. So actuators is a component that input of the actuators is the electrical signals, output of the actuators is the mechanical process. It can be rotational, it can be displacement, and so on, as long as it is a mechanical signal. But for sensors, the input of the sensors here is the physical signal. Okay, physical signal is not electrical signal, so it can be level, it can be pressure, it can be temperature, it can be any other physical signals as long as it's not electrical. And we go to the sensor, it will convert the physical signal to the electrical signal, either in voltage or current. So usually it's voltage. And in order to do system ID, generally we have a procedure for it. First is we have to do experimental, which is the process. We have to collect the input-output data, including the noise, including the output, and including the input. And this data will be lots of data. Okay, 1,000 length, 2,000 length, or maybe 10,000 length. And from the data, we will visualize it, plot it in 2 dimensions to see the Y and XY graph. Then we estimate the criteria. We select the candidate model structure and do some non-parametric analysis. For example, impulse test, squared steps test, and frequency response test. And from there, we will estimate the mathematical model structure. And in order to validate, to make sure that this model estimation is correct or not, we have to use some model quality assessment, or we call it as the model validation. For example, we have a residual analysis, estimation error analysis, and cross-validation. As long as the model quality assessment fulfill this residual analysis, error analysis, and cross-validation with a certain percentage and with a certain error, so if we satisfactory with it, so we choose that model to be the representations of the process, unknown process given. That's why in order to do empirical modeling, we need a standard sample data system. We need a computer, we need a laptop, we need an analog to digital converter and digital to analog converter. Okay, so for example here, there is a digital to analog converter to the actuator and the process. So the process is analog signals, and then this analog signal will be sampled by sensor, will be sampled by a converter, and you will convert the analog signal to voltage, and this voltage will go to the computer system, okay, and to process, and we will give the output to compare with the input and output in order to derive the mathematical model. So for system ID, involve application of concepts, basically from 4 broad fields, which is given by generally in mathematics and engineering, mathematics and statistics. So in system ID, we will do some coverage on the system and sampling theory, theory of random process, signal processing, and estimation theory. So that is the end of preamble of my introduction for the subjects. Okay, it's about half an hour. So is there any question from the student? If you want to ask, can you on video, please, all of you, because you need to introduce to me your name and what is your job, okay, and why you enroll to the master's program. We begin with the top picture. The top picture is, what's your name? Surya. Surya? Sivananta, sorry, Sivananta. Can you introduce yourself?
Good morning, everyone. Good morning, Doctor. My name is Sivananda, and currently working as a project manager in Honeywell Engineering.
Honeywell.
Yeah. I mean, the Building Management System Division.
All right. Graduate from?
Graduated from University of Nottingham. And
Nottingham,
yeah.
Sebenarnya UK
Yeah,
or Sebenarnya?
Sebenarnya.
Sebenarnya, the twin program. If you spend your time at Nottingham?
Yes,
1 year
1 year.
in UK.
In oh, you mean in UK, is it? No, I didn't go to UK.
4 years at Semenyi.
3 years in Semenyi.
3 years in Semenyi.
Yeah.
Thought you were going to UK 3+1 or 2+1 program.
I didn't. We had an option during the final year, but I didn't select to go to UK.
Okay, all right. Oh, selected only, all right.
Yes.
Umar, Brother Umar.
Test, sorry. Okay, good morning everyone. My name is Umar. Currently I'm working as instrument engineer. Usually play with LabVIEW programming.
Where about?
Sorry?
Instrument engineer, where about?
I'm from Vicinity Sdn Bhd.
This synergy.
Currently VC
Oh, VC.
Virtual Instrument System Innovation. Vicinity Sdn Bhd. Currently doing project for Petronas plant at PRSB.
First degree, graduate from?
So I'm graduated from UIA in 2017
2017.
in mechatronics.
Sivananta?
17 years.
Sivananta? Graduate what year?
2006, doctor.
2006. Oh,
Yeah.
Okay, next is next to Umar is siapa ni? Yang pakai headphone ni? Surya.
Good morning, doctor. Good morning, everyone. Okay, my name is Surya Kumar. You can call me Surya. Currently, I'm working as order engineer at Emerson Asia Pacific.
Audio.
Order engineer.
Audit.
Order. ORDER. Yeah.
Order engineer. Where?
Emerson Asian Pacific.
Emerson. Multinational.
Yes, MNC.
Okay. First degree from? First degree.
Infrastructure University Kuala Lumpur. UK.
Clio.
Come again, doctor?
KL IUC.
No, in IUKL.
IUKL.
Yeah.
IUKL is infrastructure
Ikram.
Kuala Lumpur.
Yes.
Oh, ni Ikram dulu.
Yes, doctor.
Okay. Graduate what year?
2016.
2016. Okay. So consider same age like Umar. Okay, thank you very much. Next.
Thank you, doctor.
Number 4. Hello. Number 4. Student with headphone and microphone together.
Is it me? I think so.
Daniel.
Yeah. Okay. Hello, everybody. Good morning. Assalamualaikum. My name is Daniel, and I'm working at DXC Technology as a DXC Technology. So yeah, previously it was a HP Enterprise. It changed its name. I work as a build engineer. It is more to IT. Yeah. So previously I studied in mechanical engineering at UTM, specifically in manufacturing.
Okay.
Right.
What year?
What else?
What year?
What year? 2020. I graduated at 2019. 2018. Sorry.
2018, eh?
Yep.
Okay. Your age about Kumar and Surya. Okay, thank you very much. Next, the only girl in the class.
Hello.
Yeah.
Good morning. I'm Fariza.
Okay.
I'm currently working as a service engineer
Service.
at TTES Franken.
ES.
TTES.
MNC.
No.
Local company. Okay.
Yeah. So previously I'm graduated from Uni KL MFI.
Uni KL, MFI,
Yeah.
Panjang, Bangi.
Yeah, Bangi.
Okay. What year?
2018.
2018.
Yeah.
Okay. Alright. So masih baru kerja, masih baru graduate.
1 year experience.
1 year.
Working. Yeah.
Alright. Thank you very much.
Thank you.
Next. Siapa ni? Tak kenal. T-shirt merah. Azim. Azim Jamil. Tu kartun lah. Azim Jamil. Awak punya suara macam suara kartun. What's wrong with your microphone? Nanti Hazim boleh betulkan. Siapa kenal Hazim ni? Is it your friend or not? No idea. Okay, no idea. So we take a rest about 10 minutes. 10 minit rehat. 10.55 masuk balik. 10.55 masuk.
Okay, doktor.
10 minit.
Right.
Doctor.
Okay, Bismillahirrahmanirrahim. Assalamualaikum and good morning. Boleh masuk?
Assalamualaikum. Boleh. Okay.
Okay, so I continue chapter 1, which is the introduction to system ID and estimations. Okay, so basically we are try to estimate the model, the plan. Okay, estimate the plan here, which is represented by theta, with the estimated model in yellow, represented by theta hat or theta cap. So system ID, as I told you before, involve application of concept from 4 broad fields, which is system and sampling theory, theory of random process, signal processing, and estimation theory that build up to the knowledge of system ID. And to be more details, it will be some linear modeling, least square estimation, recursive parameter estimation, model selection, self-tuning control. And we are using a software, which is a MATLAB Simulink. So all students are required to install MATLAB and Simulink in your own laptop or in your desktop. Okay, so please install MATLAB and Simulink. And then it involves some statistic, ordinary differential equations, and linear algebra. So some elements of the course, which is non-parametric and parametric modeling, least square and recursive parameter estimation, model selection, and some case study. So it will involve discrete time system ID and as well as continuous time representation. So discrete time ni adalah yang melibatkan Z or Q in discrete time, while continuous time is in S domain, in frequency domain. And system ID can be implemented in online and offline. Okay, so online meaning like this, online kita measure online dan kita proses online. Okay, but offline kita akan record benda tu, and then we switch off the equipment and we bring the data back to the home or to the office, and then we analyze from there. So that is considered as offline design scenario. So the system ID involvement, including mathematical model of dynamic system based on a set of measured stimulus and data samples. It covers a lot of disciplines, okay, which is mechanical engineering, biology, physiology, meteorology. Meteorology is something to do with weather forecast. Economics, model-based control design. So we are focusing on the model-based control design. So the concept is about the same, where you have the input, you have the disturbance, you have the output, and from there we can execute the experimental, we can capture the data, and we find the relationship between the input and output that suit the mathematical model of the dynamic system. So our subjects will focus on the model-based control design process. So it is an iterative process, dia berulang, okay, the looping, okay. So first step, we have to capture the data from the real world. Then we have to do some processing as necessary, and then we select the mathematical algorithm to identify the suitable mathematical model. As a result of that, we have to simulate the time response of the system to see whether it has some contra with other method as well. Okay. So term identification, the word identification introduced by Zadeh in 1956, it refers to the problems of determining the input-output relationship of a black box or modeling based on observed experimental data. So I can say that system ID is the process of determining by means practical testing of the transfer function or some equivalent mathematical description of the dynamic characteristic of a system component. So as you know that mathematical model-based control design, okay, can be write as the transfer function, or it can be write as the, okay. Nampak tak saya tulis? Nampak tak saya tulis? Can you see?
Yes.
And doctor.
Can you see?
Yeah, I can.
So transfer function. Okay. Sometimes we call it as a TF. Sometimes we call it as a G is the Y over U. Y is the output, U is the input. Then we have a numerator polynomial divided by denominator polynomial. Okay, so for example, S plus 2, then S plus 3 squared. Okay, so this one you can analyze in control system as 0 here over there, and then -2, and then -3. Okay, is an overlap poles at the S plane. So this is, we call it as the S plane. Okay, so this is a third order system, because when you open this one, it will become 9. Okay, it's a second order system. The other one is the state space representation. Where you have a x dot, y. Okay, so A, B, C, and D is the matrices. A is the system matrix. B is the input matrix. C is the output matrix. And D is the feed-forward matrix. Okay, this one is also a mathematical model. Okay, and the domain can be two different. One is the discrete and continuous. Okay, so this one is using S operator. This one is either using Z or Q. Some book is using Z, some books using Q. So we will go this one later on in the next chapter and other subchapter, inshallah. So why models are needed? Simply for predictions of system behavior and to design a controller. It can be PID controller, adaptive controller, self-tuning controller, and so on. So as I told you before in the previous diagram, this is the definition of a system ID, where you have a process, you take the input and output, you predict the mathematical model. Model is estimation. Approximation, estimation, simulation, or numerically calculated. But process is the real thing. Okay. So some books define system ID as the methodology for building mathematical models of dynamic system using measurements of the system input and output. Okay. So the process need to measure. You need a hardware. You need a computer. You need a A to D, D to A to capture the data. You need a model structure. Either the model is linear, non-linear, first order model, second order model, or higher order model. Then we have to apply estimation method, okay, in order to estimate the value of the adjustable parameters, because the parameters always change in value if the system is dynamic. and then you have to evaluate the estimated model so that the estimation method is verified and validated based on the evaluation analysis. So the objective of SI actually to obtain a parsimonious model and adequately representing the system. The word parsimonious sometimes is never heard before, very often. So parsimonious model is a model with few parameters, very few parameters as possible for a given quality of model. Some people define process as a higher order system. Sometimes it's 20th order, 30th order, and so on. Actually, if we look carefully, we analyze carefully, we can minimize the parameters as small as possible that represent the quality of that particular model for the process. So by given a process signal, but if we given a model structure, error criterion, and the constraint, we can determine the mathematical model that satisfies the process. Okay, so this is the diagram that I've shown before. Okay, you can see that here, this output Y and Y is not the same. Okay, Y cap or Y hat, whether the symbol hat there is the meaning of estimation, while without cap or without hat is mean for the real value from the plant. Okay, and of course in the plant there is a disturbance and there is an input from the controller with the standard references that set by the user or by the designer. So the model will transform an input signal into output signals, and this will be represented by differential or difference equation. So differential correspond to continuous time. Difference equation correspond to discrete time. Okay, so both are not the same because they are from a different domain. So the input of the system can be measurable, can be unmeasurable, can be controllable, and can be uncontrollable because we never know what will happen in the system. That's why we must understand, this must analyze the behavior under specific situations. So application of model, as I told you before, can be applied in design, can be applied in estimation, can be applied in control strategy, and can be applied for monitoring with different purposes as listed. And we can approach, okay, design the model based on two methods. One is the first principle and one is empirical. So first principle is quite tedious with full of mathematics derivations, while the data-driven is more towards data, how we handle the data, how we pre-process the data and process the data using the suitable algorithm and model structure. So we let the data speak for itself. If we take the data from a human body, it can be huge data. Okay, for example, for scanning data, we have to use an MRI because our body consists of a lot of soft tissues. If we use X-ray, that is not suitable for soft tissues. Soft tissues is something that is very soft and cannot be detected by X-ray. That's why we have to use MRI, magnetic resonance imaging, in order to detect the structure of the soft tissues in the bone or outside of the bone. Okay, so that it can be plotted accordingly. Then give a film to a doctor, and the doctor can diagnose what is the problem with our body based on the data that has been plotted in the certain pictures of film. And that's similarly to the car as well, and the car for the disabled persons. Okay, all can be captured, and the data will speak for the system, the real behavior of the system. Of course, when we compare with the first analytical modeling and empirical modeling, there is a pro and con for it. Okay, for example, in physical modeling, we try to take one example, which is the suspension system here. So this suspension system, consists of a mesh, spring and damper, and the road profile is the test process for the system under determination for mathematical model. So in this system is the passive element, which is a mesh, damper, and spring. We have a sources, we have a transducers, we have a junction structure that is physically meaningful parameters. So this is the structure of the mathematical model of the estimated suspension system, where you have a G stands for transfer function, Y stands for the output, and U stands for the input. And Y have a numerator polynomial, okay, numerator polynomial, while input U also have the denominator polynomial, okay, where A is the function of M, B, and K, as well as B as well. So empirical modeling, we assume the suspension as a black box system. We never know what's inside. We never know the coefficient of the mesh, the coefficient of the spring, the coefficient of the damper. But we know, we measure the input and we measure the output. That's why from there we can also derive the empirical modeling that represent the black box of the suspension system. If somebody told me which one is good, which one is bad, I will give the answer, both are good, both have good, and both have bad, okay? So at least here the comparison for physical modeling or analytical modeling is some advantage. We have a physical insight and knowledge, okay? We know the mesh, spring, and damper. We can refer to the manual, what is the constant, what is the coefficients. And the models conceive system before hardware is built, meaning that we can simulate the mathematical model before we design the real system that under determined. But for disadvantage of physical modeling, it often leads to a high system order with too many parameters, which is complicated. So this is not good for us, because the more complex it is, the more difficult for us to analyze the physical modeling, which input-output model has a complex model structure. So this is also difficult. Not convenient for parameter tuning, of course, when it's complicated, hard for us to do tuning, and then it's too difficult to analyze due to the highly mathematics style of derivations. But for empirical modeling based on black box, the advantage of it is close to the actual input and output behavior. So we can measure the input, we can measure the output, and we can conclude the behavior of the black box. And this black box is convenient structure for parameter tuning. Very easy to tune because we know the behavior of the black box system, and useful for complex system. If it's difficult to analyze, difficult to derive, so the solution for the complex system is just we assume it as a black box when we can build the model based on the input-output. But for the disadvantage is no direct connection to the physical parameters. Of course, we don't know what's inside the black box. No solid ground to support a model structure. Of course, we just propose a model structure. This is the model, this is a linear, this is a non-linear, okay? We guessing, well, we guess based on the scientific data, and then not available until an actual system has been built. Of course, we need the system, okay? Then we can assume it as a black box. Therefore, from there, we can carry out the protocol of the data collections. So this is the dynamic model, okay, for a car, which is a car is considered as a dynamic model because they have 4 tires, they have 4 suspensions, and the parameter of the car mathematical model is dynamic. It can change from time to time. It's based on the road profile. Okay, so since we want to derive the system ID based on input-output, so we must have the data and can be represented in continuous time and discrete time form. Okay, for example, this is the sample, okay, just now. So if you see here, we have one mass, one spring, and one damper, which is represented by its constant M, K, and C. So the force is on the left to the right, the capital F. And when it apply the force, so the mass will be displaced, will be moved to the right with the displacement of YT. So physical system like this that we learned using during the undergraduate, we can assume it as a second order system based on the second order differential equation, right? So second order system, what is the definition of second order system? The definition of second order system is a system that has two poles, okay? That has two poles, which is located at the left half plane of the S-plane. So in this case, the differential equation here is given by my double dot cy dot plus ky equal to f, where m is the spring constant, c is the damping coefficient, and m is the mass. We can solve this, okay, by using the differential equation where we assume the speed v, velocity is dy dt, which is derivative of displacement, and the derivative of displacement is equal to y dot is equal to ay plus bf, and y is equal to cy, where y of t displacement and v of t the velocity is the state variables of the model. And from there, we can derive the important metrics for the model, which is A, B, and C, which is system metrics, input metrics, and output metrics C. And we can find that this is the mathematical model, which is 1 over ms squared plus cs plus k, where s is the Laplace transform. So in other way, that is considered as a continuous time dynamic model, okay? So what is the discrete time dynamic model? So discrete time dynamic models based on the same system, mass, spring, and damper, which is we have to use a sample and hold. We have to do the sampling, which is we use ES, sampling time or time interval, okay, where this will be carried out until a certain period, maybe 1 minute or 2 minutes, there, so that we have to introduce a sequence. N is equal to 0, 1, 2, 3, 4, 5, 6 until the data finish captured. Okay, so in this case, 0, that is the initial, 1 is the first sample, 2 TS is the second sample, third sample, fourth sample, and so on. And from there, we can build the relationship between the sample input output by using a second order difference equations. So this is what I call a difference equation. Okay, you can see here is different from the differential equation. Y is the output, U is the F is the input, Y is the output, A1, A2, and B is the parameter or the coefficient that we have to estimate in order to find the mathematical model. So for simplicity, TS is taken one at a time, and the equation can be rewrite as YT, A1, YT minus 1, A2, YT minus 2 equal to B, FT minus 1. A1 and A2 is the model parameters that we are going to estimate, which is related to the system constant, mass, spring, and damper with the sampling interval TS. Okay, so the difference equation shows the dynamic nature of the model, and we can apply it in any process. Okay, so we can use a computer as well to compute the displacement at a specific time with this using this equation. So when it is in a discrete form, it's easy for us to calculate using the mathematical model and using a computer simulation. And this computer simulation can use prediction as well. What will happen in the next in the next stage of the time. So it was similar to what I described before. Okay, so we can apply identification in certain cases. Okay, for example, this is a real case taken by Leonard Jung book from the System ID, where they applied the solar heated house. So solar heated house is not suitable in Malaysia due to the fact that our weather is very hot, hot and damp. But this solar heated house is suitable for the European country where they captured the solar energy using a solar panel. And from the solar panel, they capture the energy and activate the pump. So the pump will pump the water throughout this storage, where this storage is consists of heat storage. Okay, so inside the box is filled with the pebbles. Okay, pebbles. Pebbles ni adalah batu sungai yang kecil-kecil. Okay, batu sungai ataupun stone river stone have a capability to what do you call that, save energy, save heating in that stone, and then that's why they put the stone inside the storage so that they can heat up the water, and this water will be pumped and throughout the what do you call that, the radiator in the house. So the radiator is to heat up the house. Okay, there is a radiator, is a metal radiator, and the hot water will circulate inside the radiator to heat up the house. We call it as the central heating house. Okay, but for Malaysia, this one is not suitable because we more towards to save TNB bills. Okay, so now is the PKPB in Kuala Lumpur. So everybody work from the house. So the fan is on, the light is on, the air conditioning is on. So we use a lot of energy, okay, to cool the house, not to heat the house. Okay, so this idea can be applied in case study where we use the solar panel to capture the energy, the solar energy, so that we can use this solar energy for lighting, free lighting, free fan to on the fan, and then for the water heater for the bathroom. Okay, so I can consider this one is not on grid, is the off grid implementation where you don't have to communicate with the NB anymore. Okay, you just put the solar panel at your roof and then ask somebody else, a consultant, to do the connections. So solar panel have a lot of varieties in Malaysia. So you can choose cheap one or the expensive one. Coverage how many energy that you can save, okay, to heat up your lighting, to heat up your fan, and at the same time to heat up your water heater. Okay, so it can be used in the case study. So for this solar heated house, the data captured is the storage temperature in degrees Celsius. So it's using the input signal on and off fan, and then we measure the solar intensity as well. So storage temperature and pump velocity. So the sun will heat the air in the solar panels. The air is pumped into a heat storage box with pebbles, and the stored energy can be later transferred to the house. We are interested to know how the solar radiation, omega T, pump velocity, U of T, affect the heat storage, okay, temperature Y of T. That is a sample for the solar heated house. And the other one is the Swedish fighter aircraft. Okay, since this is for the aircraft, you can apply it in the aircraft to construct the mathematical model. We know that the hardware of the jet fighter is complicated. So what we need is a data on the pitch rate, leading edge flap, elevator, and cannon. Okay, all data in voltage versus time. Okay, to compute the mathematical model. And example 3 is we can apply ID in the laser eye surgery system. where this system is used by ophthalmologists ataupun pakar mata, okay, where it can remove the cataract from your eyes. For those who don't want to wear spectacles anymore, okay, so you can do this operation. We call it as a LASIK surgery using laser. This laser system will cut all your cataracts, so you are not short-sighted anymore or long-sighted anymore. Will remove by the laser, okay, but this one will cost quite high. The left eye maybe 5,000, the right eye maybe 5,000, so total of 10,000 is needed to to run this surgery. So one thing is the hot air blower system that used in many industry to heat up something, okay. So hot air blower system also the system that is under study in our subjects, okay. We will analyze it and we will apply the system ID theory in order to do the mathematical modeling of a hot air blower system. Example 5 is the hydraulic actuator system. All right, so this one is the actuator, is the hydraulic base. We use oil as the medium. So the input is the electrical signal and the output is the linear displacement of the shaft of the actuator, okay, to move forward and backward. Of course, in order to do this, we need a cylinder. We need a proportional valve as the controller, and we need a positional transducer that measure the displacement of the shaft of the cylinder. Okay, so it can be LVDT in order to measure the displacement, or you can use any sensors that can measure displacement. So there is a video for it. I'm not sure whether we can run it or not. I believe we can't. It's in another file, never mind. We can show it later in chapter 5. Okay. So another one is the pneumatic actuator system. This also actuator, but the medium is not hydraulics. It's not using any oil. It's just using pressure air, okay, as a pneumatic actuator system. So this system can do some displacement as well, where we use the electromagnetic sensor to measure the displacement with the pressure sensor and with the control valve as shown. Video for this will be shown in chapter 5. And a DC motor as well. Okay, so DC motor is common thing in electrical, electronics, and mechanical engineering system, because motor are used for several things in the robotics and so on. So how model are used? So as I told you before, model applied in scientific modeling, prediction and control, state estimation, fault detection, and some simulation and operator training for monitoring system. And is can be models. Some writers said can be a cognitive model, normative model, descriptive model, and functional model. So actually we are on the number 4, which is functional models for action and control oriented. So cognitive usually refer to the human concept. Normative usually offer to the purpose oriented. Descriptive is always correspond to the behavior orientations. So, but to determine the model, it can be by implementing knowledge of laws and nature and experimenting on the process. So both can be done. Both can be applied in knowledge type model and dynamic control model. The important thing is whether we must understand and how to differentiate a linear and a non-linear model, or whether it is a parametric or non-parametric model. So this chapter will be discussed more detail in chapter 4, where we have to estimate the parametric methods, okay, in order to get to estimate the parameters. And then this method basically is more popular compared to the non-parametric method because parametric identification method involve a lot of calculation with a higher accuracy compared to the non-parametric method, which is just using graphics. Okay, so non-parametric method use a lot of graphics, especially in time response, frequency response, impulse response, and power spectrum density. So we drag out information from this graphic, then we estimate the value and parameters and construct the mathematical model. This is the sample of it, where you have a step response, impulse response, frequency response, cross correlation function, and the power spectrum density. So non-parametric method is always use a graphics picture in order to estimate the model, which is cannot easily use for simulation and control design compared to the parametric method. But parametric method is something like this, no graphic, just equation, difference equation. For example, you have a finite impulse response, y is equal to u minus 0.3, 0.1 u and plus e. E is the noise or disturbance. So if you have this equation, so easy for us to do the simulation using a computer program. So the range, the spectrum of the mathematical models can be shown here, where start from the left, which is the black box, and ended at the white box. So it based on the difficulty or the complicated of the system. For example, electrical circuit is easy because we know the value of resistance, capacitance, and inductance, similarly to the mechanical system and chemical system. But it goes to biological systems, so this is getting more difficult because it involves a lot of human, a lot of animals, and so on. Then economic system, because the system is not stable. We are using a US currency, so US currency is not fixed. Sometimes it goes up and sometimes it goes down, so it affects the price of the price of goods, okay, in all over the world. And then the social system is more difficult because we cannot see behavior of people, and especially on the psychological system. So to test the characteristic model, okay, using a parametric model, so we can use some property, okay, instead of number different terms, impulse, step, frequency, and zero pulse. We also can use the ARX model to evaluate the numerical value of the coefficients and the time delay in the certain system. For example, impulse response of a dynamic model is the output signal that results when the input is impulse. So impulse signals, okay, if I show here, impulse signals, okay, so you have the unknown system here, and you have the injection. So impulse is something like this, very, very narrow with pulse, okay, and it can be plotted, okay, can be plotted like that. So that is the output of the impulse. So usually the best thing is we use a square wave, okay, so that you can see the response much better compared to the impulse. Impulse, some people not using it because it's too fast compared to the square, where you can control the speed of the square wave during the injections. So this is sample of the unit step response. Okay, you can see that the difference between the impulse response and the step response. And this impulse response, the value of it is delta is equal to 1.4 or 0.25. compared to the unit step response. So unit step response is using a 1 volt square in the injection, we assume with the noise-free system. So step response, much popular, much easy to use compared to the impulse. Both are called transient response. But for the other one, frequency response is using a sine wave instead of impulse, instead of a square wave. So you're using square wave, then we generate the, we capture the output, which is the voltage output, voltage input, and the phase difference between the input and the output. Then we will produce something like this, a Bode plot, which is decibel versus frequency and phase versus frequency. This is a sample of the frequency response of 1, 2, 3 is a 4th order system. And of course, when you have the mathematical model, you can differentiate the zeros and poles by split it, by factorize it. Okay, then you can plot it in the S-plane. For example, here is the symbol of square is the zeros, and the symbol of cross is represent as the poles. So identifying a system from the empirical data, generally we need a knowledge. Okay, we have to gather all the knowledge, early knowledge, or we call it the prior knowledge, before we do the experimental for the system ID. So therefore, we must categorize what's the system, whether it is a white box, a gray box, or black box. Depends on the prior knowledge. If you have a lot of prior knowledge, 100% or 90% above prior knowledge, so you can use as a white box approach, which is more easy. Okay, first principle information used to derive the full model. So system ID can be used to reduce the order of complexity. But if your prior knowledge, okay, is below 50%, so that is what we call that a certain structural information, where the model is already available, but the remaining 50% is unknown. So that is the challenge to use the system ID. And the black box is considered as you have a zero knowledge, no prior model available, and both structure are missing out, no idea about it. And this is the challenge that we have to face. We have to design the system ID algorithm in order to cater for these black box problems. So the explanation of it is in the next slide. You can read by yourself. Okay, the gray box problem and the white box problems. So as can I conclude about it? So transient response is the pre-method for system ID before we apply special signals to identify the system. So from the transient response, from the pre-testing, so we can know the behavior, whether the system is first order, second order, or high order. The frequency response is to see whether there is a time delay in the system by looking at the phase response or the frequency response, whether it is flattened at minus 180 degrees or below, more deep compared to minus 180 degrees. Then we have checked whether the system have a disturbance. If the system have a disturbance, we consider it as a stochastic steady state information. And we have to use the pseudo-random noise data, which is a PRBS, in order to generate a model. So which one we will choose, either analytical or empirical? So I choose empirically because it saves a lot of time, a lot of headaches gone, because we just construct the plan here, okay, the unknown plan. So we set up the computer, which consists of A to D, D to A. Then we generate the excitation signal, and then we design the identifier algorithm. Then we get the mathematical model. This identifier algorithm is have a simple one, complicated one, but those who are further studies for PhD or masters, so identifier algorithm is the considered as the significant or findings for the masters and PhD levels. Okay, so that is the system being identified, as I told you before in the previous hour, where we have sensors, actuators, and process, including disturbance in the real system ID. And to do that, we need a procedure. Okay, so the procedure is we have to gather the data, we have to do the model structure selection, we have to do the model parameter estimation, and then we have to do the model validation in order to check whether the model is accepted or not. By using a standard sample data system, we can accumulate all the data. So this is a very important. We have to choose what is the suitable sampling time in order to sample the data of input and output from the unknown process system. In order to do that, we can use two software available. One is LabVIEW and the other one is the MATLAB System ID Toolbox. So I prefer to use MATLAB System ID Toolbox using a MATLAB Simulink. So we will use this software, okay, in order to estimate the mathematical model of the process. So please install this software in your laptop. We will use it in chapter 5 in the real case study. So I can say that steps in system ID consist of data collection, model presentations, choice of criterion fit, parameter estimation, and model validations. Or you can simply use as 4 steps, okay, also can. And then the explanation of it is shown here, okay. What is each of the protocol, okay. So this one also the same explanation for each protocol, and the important thing is the data must be reliable, the data must be correct in sampling, okay. So usually the sample time is based on the time constant. Rule of thumb is between 4 to 10 sample points over the rise time. So the data must be recorded, okay, must be make sure the signal to noise ratio is high as possible. Okay, if the signal to noise ratio is low, so most probably there is a noise in your system. Then we choose the input signal. Okay, the suitable input signal is the PRBS, pseudo random binary sequence, which we will learn in chapter 2, inshallah. Okay, how to generate the pseudo random binary sequence. And then we propose what do you call that? Model structure or candidate models. Okay, whether it's a model of ARX, RMAX, NURMAX, and so on. Then we estimate the parametrical model using the estimation method, which is a recursive method. Okay, is a lot of mathematics here. And then we estimate it, and then we make a validation to make sure that the model is correct based on the validation criteria. Usually this one is using a statistic. Okay. This is some of it. Okay, so some basic question of the system ID you can read about. Okay, the question and the answers. And common terms using for system ID: estimation data, validation data, models view, data views, model set, model structure, and so on. And some exercise. This exercise is based on the book chapter, which is chapter 1, part 1. Okay, for details, you can read the books. Okay, read the books and then can answer some of the questions. Right. Is there any questions? Ada soalan nak tanya? How to install MATLAB? How to install
So far tak ada.
LabVIEW? Saya tak pakai LabVIEW sebab LabVIEW ni dia susah sikit nak pakai sebab dia ada pakai dongle dan dia ada banyaklah isu-isu yang susah kita nak atasi. So we are using MATLAB. I hope you install already MATLAB in your laptop. Have you done that?
Not yet.
Not yet. So, boleh tak install the MATLAB?
Sure, Doctor.
Sure. Can?
Okay, Doctor. Sure.
Okay. So I will stop here. Okay, I will stop here because at 2 p.m. I have a class. I have to prepare for the class at 2 p.m. So we will resume the class tomorrow. Okay, tomorrow, 22nd of November, on Sunday, start at 10 a.m. Okay.
Okay, doctor.
Okay,
Doctor.
so
Okay.
I will share the YouTube link later on. Okay, so I'll see you tomorrow at 10 a.m.
All right, doctor. Okay.
Thank you very much.
Thank you, doctor.